All right, so we looked at some examples, and there's no fixed way of finding, the lambda values and stuff, but you just have to kind of figure out a way to eliminate the variable. So let's look at one more example. Finding points on this sphere, which are closest to and farthest from a given point, 3, 1, -1. So as always with distances, the distance is x minus 3 for any point on the sphere. But instead of working with square roots, because we will be taking partials in the form of gradient, we will just call this capital T and work with a linear equation. Sorry, not linear, but equation without a square root. Okay, so this is now our optimization function. So we got to maximize or minimize these, and the constraint is that the point we should be on the circle sphere. So this is my del f, so I'm called this f and I'm going to call this g, is going to be 2x minus 3 and then 2y minus 1 and 2z plus 1, and the gradient of g is going to be 2x, 2y, 2z. So what are the equations that need to be satisfied? So I need 2 times x minus 3 to be 2 times lambda x. I need 2 times y minus 1 to be 2 times lambda y. 2 times z plus 1 to be 2 lambda z. And I need x squared plus y squared plus z squared to be equal to 4. So we have 4 variables and 4 equations, which means we can solve this. Right, so let's see, what does this give? This gives me x minus 3 is x times lambda. So if I solve for lambda, if I solve for x is going to be 3 over 1 minus lambda. This will give me y minus 1 is y lambda, and y would be 1 over 1 minus lambda. This will give me z plus 1 is z lambda. So z would be -1 over 1 minus lambda. And then if I take all 3 of these and I plug it in here, because of the constraint, I will have this squared plus this squared plus this squared should equal 4. So you have a common denominator, and then a 9 plus 1 plus 1. Cross multiply 1 minus lambda whole square should equal 11 over 4. So that gives you 2 possible things now. Remember, this is not we're not talking about a particular box. So we can have negative values. So lambda is 1 plus minus square root of 11 over 2. And then once you have your lambda, you can find each of your x, y, and z, because you have x, y, and z in the form of, you have a relation between x, y, z, and lambda. Right, so it looks like all of the denominators have 1 minus lambda. So 1 minus lambda is the square root 11 over 2. So x is 3 divided by square root 11 over 2. So 3 times 2 square root plus minus. And then y is 1 over, so this just becomes 2 over root 11 plus minus. And then -1, so minus plus root 2 over 11. Okay, so there's going to be 2 of these points, right? So the 2 points that we have are 6 root over 11, 2 over root 11, -2 over root 11, and -6 over root 11, -2 over root 11, and +2 over root 11. Okay, now the last thing you do need to check need to check the value of f, which is d squared, at each point, and one will be the max and the other min. Right, so for that you're going to have to plug these things back into this expression, which is the distance. Okay. The last thing that remains for us to do is Lagrange multipliers, but with two constraints. So basically the problem will be is to maximize or minimize some function f subject to this and another level surface h, which equals some other constant c. So here we will require that the gradient of this function is some lambda times the gradient of the first constraint plus some other constant u times the gradient of the second function, or the second constraint, or the second level curve. So which means this amounts to solving 5 variable in 5 equations. What are the equations? Well, we will take the x component, compare it with the x component of each of these, the y component with the y component of the gradients of each of these, the z component with the z component of the gradients of each of these. And then we have the constraint 1, the level curve, and we have the constraint 2, the level curve for the second one. Okay, and as you can imagine, this process can be continued if you have multiple constraints. So let's look at an example. Find the minimum or maximum value of on the curve of intersection of x minus y plus z equals 1. So that's your first constraint, and x squared plus y squared equals 1. That's your second constraint. So as before, I will find the gradient. That's going to be 1, 2, 3. Then I'll find the gradient of the first constraint. Let's call this g and let's call this h. That's going to be 1, negative 1, 1. This is going to be 2x, 2y, 0, because there is no z component there. And so I have 1 is lambda plus 2x mu. 2 is negative lambda plus 2x, 2y mu. 3 is lambda because there's no more mu, and then x minus y plus z is 1, and x squared plus y squared is 1. So here, one of them, actually this, is already giving me lambda. Okay, so that's a good thing. So we have 1 equals 3 plus 2x mu, or x equals negative 1 over mu. Okay, there's one more step here. You get negative 2 equals negative 2x mu. Divide, you get x is 1 over, wait, this is positive. So negative 1 over mu. Putting it in the second equation, you get 2 is negative 3 plus 2y mu. So 5 is 2y mu, and y is 5 over 2 mu. Now you can plug this into this last equation for x squared and y squared. So 1 over mu squared plus 5 over 2 mu squared equals 1. So you have 1 over mu squared plus 25 over 4 mu squared is 1. Common denominator is 4 mu squared. It's 4 plus 25. 4 mu squared is 29. So mu is plus minus root 29 over 2. So what does that give us for x and y? X is reciprocal, so plus minus 2 over root 29, and y is reciprocal but with a 5 over 2, so the 2's get cancelled, so it's 5 root 29 plus minus. And z can be found using this one, which is 1 minus x plus y. So it's 1 minus 2 over root 29 plus 5 root 29. Should be root 29. Root 29 minus 2 plus 5 times 29. I think I made a mistake here. Y is 5 over 2 and divided by, so 2 over root 29. Oh, so 29 is in the denominator. Yeah, that makes more sense. So plus minus, this becomes 1 plus minus 7 over root 29. Okay, so you have your values for x, y, and z, and then, but you still do need to evaluate at to get the max and min values. So that's it about Langrange multipliers, and they can be extended to more constraints, but we will limit ourselves to 1 or 2 constraints, mostly 1 constraint for now. Okay, that's all for this video.